Alrighty, my friends. Good morning. Good morning to you all. How are you? I hope that you're doing well. I hope that you're healthy, happy, safe. I am very happy to be here. I wish, of course, that I could be there in person with you, but of course it's been a weird year, more than a year now, and I'm sad, but I'm at least here in online. I'm very happy to be here with you. I'm in San Francisco, California, here in the United States, so it's 5 in the morning, and I have not slept very much to be able to make this meeting. So thank you so much for having me. My name is Josh Long. I work on the Spring team. I have been on the Spring team since 2010. I am a Spring developer advocate, an open source contributor, an engineer, a Kotlin Google developer expert, a Java champion, and I am at your service. And if you have questions, if you have comments, if you have ideas or anything like this, please send me a message on Twitter or email me. I'm very happy to talk. There's also my Git repository for this presentation, where we're going to look at a lot of different things. And so, you can find the code there for your own reference. I used to travel, but I still am very lucky to be here in different conferences worldwide, virtually. I have done training videos. I have a book called Cloud Native Java. I did a podcast. I do a podcast every Friday. I have a podcast called A Beautiful Podcast, where I talk to people in the ecosystem. I have a blog every Tuesday. That's today, Tuesday, and so I will write one later today, called This Week in Spring on spring.io/blog. I have a screencast called Spring Tips, which is a YouTube series. And I have a new book I wrote called Reactive Spring. And this book is all about how to build reactive applications. And so, I'm out there, I do a lot of things with software, but through all the things that I do, and considering all the things that I do, the thing that is most important to me, the thing that I care about the most, is helping people build software for production. I love production. I love seeing my software delivered into production, where it can help the users that want that software. And I think it's a very exciting thing to do, to build software that people use, to see that software be useful for people. But I know that a lot of organizations struggle. They know that they want to go to production more quickly, but they struggle with how. And one of the reasons that they struggle is because it's hard to get software into production safely. They also know that they need to do so in a repeatable, reliable, efficient manner. And this is what I mean by cloud native, right? We're going to talk about that today. We're going to talk about how to build software that is intended for production, that goes to production reliably. This is not easy to do. There's a lot of things that go wrong when you start to build services at scale in a production environment. Today, these days, production, as often as not, is a cloud environment, right? It's a production environment based on something like Kubernetes and so on. And so it's a very dynamic, very distributed environment. And when you write software intended for that environment, things can go wrong, right? Things can go wrong. There's a lot of things that can go wrong. So people look for ways to go faster. They look for ways to go to production more efficiently, more quickly. And the reason that they want to go to production more quickly is because they want to improve their organization, right? And by the way, I have no slides. We're just talking, okay? Just a few minutes here. There's nothing on my screen, right? It's just a mouse pointer. So don't worry about that if you can't, there's nothing happening, okay? So they want to go to production more quickly. They know that they need to go to production more quickly. They know that the ability to deliver software into production means that they can make a change and deliver the change, validate the change, and grow. They can incorporate the learning from whatever they did in production into the next release and improve it and build something even better. This cycle of writing something, delivering it, improving it, writing something, delivering it, improving it, that cycle goes on and on and on, and it results in better software. This cycle is very, very hard This cycle is very hard to do in a reliable, repeatable manner, but they know that they must because it allows them to deliver software faster, to grow as an organization, to become a learning organization. And that's really the most important part here, is we are going to do everything that we can to deliver software so that we can grow as an organization. That's the goal here, is to find ways to quickly and consistently improve our organization. And so organizations look for ways to deliver software into production, but they see that there are a lot of things that stop their movement, the evolution of software. They see that there's a lot of things that have to happen between an idea and the customer, from code to customer. And these problems, these things, there are many of them, many different things. First of all, they know that they have large code bases. And if you have a large code base, then you probably have a lot of people working on that code base. And this is the first big problem. You see, the more people working on the code base, the harder it is to make a change to the code base and then deploy it to production. So organizations look at their large code base and they look for ways to break it apart so that they can have smaller teams. The smaller the team, the easier it is for them to deliver into production. They look for ways to break apart their large teams into small teams. And of course, in their code, it's not always easy to find a place to decompose their application. And so they look for ways in the code base to find clean lines, clean cuts to decompose. They look for something called a bounded context. A bounded context is a part of the domain model that stands by itself. It needs no other part of the application domain to do its work. A bounded context is a design pattern from Eric Evans's book, Domain-Driven Design. This design pattern is meant to describe a part of the domain that is isolated, that is insulated, that needs nothing else. If you can identify bounded contexts, then you have a natural line, a natural place to decompose, to break apart your large monolithic code base. Now, the benefit of this is that now you can have small teams. And of course, you may say, well, what is so important about small teams? Well, a small team means that you have fewer people required to stabilize, integrate, and deploy changes. This means that you have less requirements for communication, less meetings, less integration from one team to the other. Small teams are able to move more quickly. They have a very fast cycle because they're not waiting for everybody to stop doing something so that they can deliver. And in a small team, the question then is, how small is small? Well, Amazon, they talk about 2 pizza box teams, a team that is small enough that they can feed everybody with just 2 boxes of pizza. Now, you may wonder how much a box of pizza will feed. Well, here in the Pacific Northwest, here in the United States, they were talking about 5, 6, 7 people, right? About 7 people. And this includes product management, user experience, developers, designers, testers, administrators, etc. All working on one thing, one bounded context. It's very important that this small team is able to deploy software without waiting for other teams in the organization. And so it's very important that the software be independent and independently deployable so they can deploy without waiting. Well, of course, you don't have independent deploys with .dlls or with jars as class path libraries. This doesn't work because I must wait for all the class path libraries to stabilize before I can deploy my monolithic .war.ear or something like that. So that won't work. It has to be a separate service. And how do these services communicate with each other? If they're not in the same Java virtual machine, they communicate with each other over the network. This is where you get into some trouble because now you have network services, right? Small bounded contexts talking to each other over the network. These are microservices. That's the definition of a microservice. And this microservice is doing network computing, network interactions. And here we have problems because once you introduce a network into the system, you have complexity, the complexity that comes from building distributed systems. This is a problem, right? Things can fail. They will fail. And you will start to see that the patterns that we have relied upon traditionally to build software no longer work in this new environment. So things like traditional blocking I/O, imperative I/O, using Java I/O input stream and output stream, these patterns start to become problematic in a world before Project Loom, right? Project Loom will help us a little bit, but not very much. there are some problems with this traditional approach to I/O because you are waiting for the I/O to happen. You use Java I/O input stream, and you say, I want to read the input stream 1 byte at a time. While you're reading that data, the thread that you're using to read that data is blocking. And this is a problem because you cannot use that thread for anything else. You're blocking, you're not able to reuse that thread. That thread is expensive. And so you cannot scale if you're stuck blocking. All these threads are being used waiting for data, but there's nothing actually happening. And so you waste resources this way. Another thing that we can do to fix this is to use non-blocking I/O. But here we still have problems because if we use non-blocking I/O, we still have the problem of, okay, what happens if the producer of the data gives me too much data? Well, now I have a state machine I need to write. And we also have the problem of what happens if the network is not working? What happens if the service is slow? All these kinds of error situations are important to address in a distributed system. So what we need is a programming model that allows us to reuse threads to get resource efficiency, to handle errors to get reliability. And since we're dealing with lots of different kinds of data coming from the network, we have message queues, REST APIs, databases, WebSockets, service and event streams, etc. We also want something that allows us to compose different streams of data in one consistent fashion. Well, this is reactive programming. Reactive programming is a great way to build cloud-ready software. And then if you combine that with Spring Boot and with these other technologies that we're going to look at today, you have a great way to build software intended for Kubernetes. So that's what we're going to do, my friends. We're going to build some software, and we're going to do that, of course, by going to my second favorite place on the internet, start.spring.io. Okay, so we're going to build something here at start.spring.io. This is, as I say, my second favorite place on the internet. My first favorite place, of course, is production. I love production. You should love production. You should go as early and often as possible. Bring the kids, bring the family. The weather is amazing. It's the happiest place on earth. It is better than Disneyland. So we're going to build a brand new service here called the customer service. And we're going to use Lombok, which is a compile time annotation processor. We're going to use the reactive web support. We're going to use R2DBC, which is a reactive SQL database abstraction. We're going to use H2, which is an in-memory SQL database. We're going to use the Spring Boot Actuator. And that's it, I think. I'm pretty happy with those choices. We do, of course, have the choice of which packaging we would like to use, .jar or .war. Obviously, .war makes no sense in 2021. There's no use for that, right? Nobody deploys to .wars in a standalone application server. It creates unnecessary complexity in a system. It's an extra moving part whose library class path could fall out of sync with the application class path, causing fragility in production. So this is a big part of my personal philosophy of make jar, not war. And again, lots of things that you could do, but I encourage you to leave it here and accept the defaults. The next question that we have is, what version of Java would we like to use? Java 16, of course, is the current supported version of Java. Java 11 is the current long-term supported version of Java. And Java 8 is an old, creakingly old, irrelevant, way past its prime version of Java. So my friends, I encourage you to use at least Java 11 or 16. You see, Java 11 and 16 are technically superior in every way. They're faster, they're more robust, more secure, more performant, more syntax rich. They are better technically in every way. They're also morally better in every way. You see, my friends, you will not be ready for this look of sadness and despair in your children's faces when they see that you're using Java 8 in production. Don't do it. Do the right thing. Be the change that you want to see. Use at least Java 11 or 16. So I'm going to leave those as they are. I'm happy with that. We'll go ahead and hit generate. And I'm going to download this. UAO customers.zip. Okay, so my application has started. Almost. Okay, so we have a brand new application, and we're going to build a simple application that talks to a SQL database. This database will have data in it that we will describe with an entity, class customer. So our entity will have a mapping. So I'm going to give it a primary key and a name, okay? And this ID will map with a SQL ID, okay? So a primary key. This class, of course, is going to need getters and setters and toString and equals, hash code, blah, blah, blah. All this is very, very okay, but it's very ugly code. So instead of doing all of this, I like to use Lombok. Lombok is a compile time annotation processor. You can use that to synthesize the getters, the setters, the toString, etc. Then we're going to create a repository to deal with the boring read, write, update, and delete data management lifecycle. Okay, so this is going to be a repository that manages the access to that data. Then we're going to create a thing to allow us to write that data to the database. So what I'm going to do is I'm going to create a bean of type application runner, and this is a callback interface. It's an object that Spring will invoke when the application starts up, and we're going to inject a reference to our repository. And here we can write some names of people on the Spring team to our database. Now, we're going to use this repository, and you can see that this repository has different methods to support interacting with our database. Methods like save, save all, find by ID, check it if it exists, find all, delete, count, etc. All these methods, I think, are pretty familiar. What may not be familiar are the parameter types. You can see that it has something called a publisher. A publisher comes from the reactive streams specification. Let me make this a little bit larger, friends. A publisher comes from the reactive stream specification. A publisher is a type that publishes asynchronously data to a subscriber. The subscriber subscribes to the data, and when it first subscribes, it is given a subscription. We will come back to this in just a second. When the publisher produces new data, that is communicated here in the onNext method. So any new record, the first record, the second, the fifth, the millionth, the billionth, the infinite record, all these are communicated here. When there are errors, those errors are communicated here. And finally, when the processing is done, that's communicated here. So the subscriber is given a reference to this subscription. This is very important. This is, I think, the most important part of the Reactive Streams API. This subscription is what the subscriber uses to request more data of the publisher. The publisher might produce too much data. So instead of overwhelming the consumer, instead the subscriber uses the subscription to ask for, let's say, 10 records or 1,000 records or a million records or infinite records, right? So you can request as much as you can handle and no more. This allows you as a consumer to ensure that your service doesn't fall over because it is overwhelmed. If the subscriber, if the producer has produced too much data and the subscriber wants nothing more to do with it, it can cancel that stream. So this allows the subscriber to control the speed, the rate at which the producer publishes its data. This is very important. In a distributed system, it's very natural. When you do network programming, TCP or UDP programming, there's a state machine that you must write to handle the scenario when the publisher produces data faster than the consumer can handle it, right? That's very, very hard code to write, but you must do it in order to write proper networked code. That state machine is just, it's the same thing as we're doing here. When you build a distributed system at scale, it's very common to use a message queue. Message queues introduce a buffer to absorb extra load so that the consumer can consume the data from the buffer from the message queue at the speed it's comfortable and no faster. The same idea, the same principle. The consumer is is controlling the speed at which it consumes that data. This is called flow control. Sometimes you will hear this concept of the subscriber controlling its own rate of consumption referred to as back pressure. Okay, so back pressure and flow control. These are very basic ideas, and they're very important. They're a very important part of the reactive streams abstraction. The reactive streams types, by the way, are a generic effort from the Spring team, from Lightbend, from Netflix, from the Eclipse Foundation. They represent an effort to describe asynchronous, potentially unlimited streams of data. And because we have one abstraction, one type, the reactive streams types, life becomes very easy to think about eventually, right? Because now you don't have to deal with all these different APIs. You don't have all these different abstractions that allow you to model different kinds of streams of data. Instead of having the RabbitMQ API and the JMS API and the Apache Kafka API and the server sent event API and the WebSocket API and the REST API and so on, instead of having all these different APIs that give you asynchronous streams of data, instead you've just got publisher, okay, and subscriber. And these are this means that it's very easy to compose these different streams, to do things with them. These types are foundational. They're very basic, and they're so foundational that they're actually part of the JDK. So Java 9 and later, Java util concurrent flow dot processor, flow dot subscription, flow dot subscriber, and flow dot publisher. These are all part of the JDK as well. And so you can actually convert one to the other by using this type, or reactive streams flow adapters to publisher, and that gives you a reactive streams publisher. Or you can go the other way around. You can go from reactive streams publisher to a Java 9 publisher. So the reactive streams APIs work with Java 8. Eventually in Java 9, they added these types, so they're interchangeable. Now these are very foundational, they're very basic. There are two specializations, two subclasses that are very interesting here. And they come from a project called Reactor. The first type is a mono. A mono is a publisher that produces no more than one record, so either 0 records or 1 record. This is still a reactive stream. It supports back pressure, but it also has support for these operators: create, defer, from direct, map, filter, flat map, etc. There's also another reactive stream here called Flux. And a Flux is a publisher that produces 0 to n values, where n is potentially unlimited. So this is also a reactive stream. It has different semantics though, right? It's just like mono, they're both reactive streams, except that mono does no more than 1, whereas Flux can do unlimited. It can do 5, it can do 1,000,000, it could do infinite, right? So these are both reactive streams, but they have different semantics. And this is very good because when you're dealing with data, you can say, I want to find 1 record. Okay, I will find a mono of a customer. I want to find all the records. Okay, I'll find a flux of a customer, right? So this is very useful for describing the semantics of our data access. So now that we have this, let's go ahead and write some data to the database. I'm going to create a reactive stream of people whose names are on the Spring team. My name is Josh. It's so nice to meet you. We've also got Madura, we've got Elia, we've got Olga, we've got Dr. Sire, we've got Violetta, and we've got Spencer. Sure. Okay, so there's 8 names of people on the Spring team. Good. Now we want to take those names and map it into a stream. Okay, name, customer, and this gives us a stream of customers, right? And you can see we have a reactive stream of customers there. Now I want to save each one of those to the database. So I'll create another stream. I'll say saved customers dot, and I can use map. I can try to use this. Let's see what happens, right? We'll say repository.save. Well, what happens there? Well, you see, customer.save gives me a mono. It gives me a reactive type. And so map takes this and maps it to another container type. And this container type is a reactive flux. So I have flux of mono of customer. I don't want 2 reactive streams. I want just 1. So I'll use flat map, right? Flat map lets me unpack or resolve the inner reactive type. So now I have just 1 kind of stream, a flux of customer. Unfortunately, this will not work for a couple of reasons. The first reason is that I need to also initialize my database, right? So I'm going to use the DBC database client, the reactive database client. And so we'll say DDL equals dbc.sql, create table customer, ID serial. Okay, primary key, name varchar, not null. Okay, rows updated. There's this. So we have now a reactive stream. We have DDL. Okay, so we have the DDL. This still will not work because you see we have these reactive types, but nothing will happen unless you activate them, right? So you have to say saved dot subscribe. Then and only then will something happen, okay? But subscription is asynchronous. So there's no guarantee that if I do DDL.subscribe, there's no guarantee that this will finish before this does. So we have to use the operators to chain these things to make them happen in a sequence. So then many saved, okay, etc. The other thing I want to do is I want to also make sure I get all the records back. So I'll say repository.find all. Okay, so now I have three things I want to happen. I want the DDL to be created first, then I want to write the data to the database, and then I want to read all the records back and print it out. So I will say DDL dot then many saved dot then many all dot subscribe. Okay, system out print line. Good. So there's our reactive stream. There's our stream of results going back and forth. Okay. Now, of course, you can write this a little bit more cleanly if you want. You can compose these things in one stream like this. In this case, I have now this one. So I say names. So okay, I'm chaining these things together. So now I have three different steps, one happening before the other. I'm using the operators, and then for the once I subscribe, the results will come back and I can just print them out here. Okay, let's run this code and see what we get. All right, there's our data. It worked. We have our data. It's up and running. We have the 8 records in the database. Everything is fine. So now I want to build a REST API, okay? And this is easy. We can just build a REST controller, customer REST controller, private final customer repository. I'm going to say customers, publisher of customer. Okay. Good. Good. So there's our customer repository integrated into our REST controller. Let's go ahead and restart this. Okay, good. So there's our code. Now we can go here, localhost customers. This is our API and it's working, right? So of course, very easy to work with. We didn't write a lot of special code. It looks very similar to non-reactive code. And that's by design, right? It's still the same familiar Spring APIs. Are we ready to go to production yet? I say no, of course not. There's a lot of stuff that we need to do to make this work, right? A lot of stuff that we need to do besides just building the API. We need to make this support observability. And one way we can do that is with the Spring Boot Actuator, okay? So Spring Boot Starter Actuator. These are a set of managed HTTP endpoints that give us information about the health and the state of the service itself. And I want to expose all, for our demo, of course, this is not very secure, but for our demo, I want to expose everything. I want to show all the health details, right? So I'll say show all the health details for the actuator endpoints. And I also want to enable the liveness and readiness probes, right? So I'll say probes equals true. And you know, Spring Boot supports dynamic configuration. So I can say, you know, conditional on platform. I can say I want to enable my pipeline, my configuration only, like Everything after this is available only when I'm running in Kubernetes. And so there, maybe I can say, like here, I could have this down here like that. That way, this would only be available, these Kubernetes probes would only be available inside of Kubernetes. But for our purposes, since we're not running in Kubernetes and we want the demo, I will run it like that. Okay, so we've got this. We can also specify things like which port we want the application to run on, right? So 80, 81, 80, 80, whatever. I'm happy with this. So let's go ahead and restart. Let's see what happens. Okay, so customers, good. But now we can go to the Actuator, and you can see we have managed HTTP endpoints, like the Actuator endpoint, the Beans endpoint. Beans gives me a listing of all the Java objects that Spring has and the relationships to each other. Are they singleton? Which class has them? What dependencies do they have, etc. The caches endpoint shows me all the application caches, the cache manager implementations for things like Hazelcast and Redis and so on. We have the health endpoint, and we'll come back to this in just a second. We have the info endpoint. Info is where you can put information to identify your service. So imagine you've written some code, you do git commit and git push, it goes to the CI environment, and the CI environment looks at the code and it creates an image and it deploys that image into production. Now there's a bug, you found something wrong. What version of the code is running in production? Well, you can look at this info endpoint to identify the service. And you can do lots of interesting things here. You can say info dot, message, right? Equals hello world, right? Istanbul, okay? So I'm gonna create a message there, right? That's one thing you can do. But you can also customize this info endpoint using the Spring Boot build. You can actually customize it to include the commit information for the Git project, the Git repository. So I will go back here, plugin. Okay, there we are. So there's this. Now I have the Git commit ID plugin. It's just added to the build. And what I want to do is add this to a Git repository. So I'll say git init, git add, git status, git add, GI, okay. Commit, -a, up, good. Now I can do Maven, skip tests, for speed, clean package. And this will compile the code, and it's going to create a file called git.properties. And that git.properties lives in the target directory. Okay, and this git.properties has information like the host, the time, the commit, the tag ID, the commit ID, all this stuff, that's very useful in identifying the service. Okay, so now we've got this. Let's now run the service. You go here, and you can see it says, hello Istanbul, that's my message. But also, we automatically get this information about the service itself, what the branch is, what commit ID, etc. So this is very useful to understand what version of the service is running. Okay, so we've got conditions, which tells us all the different conditions, all the different true or false decisions that were made by the application when the application started up. We've got the config props endpoint, which tells us all the different properties that Spring Boot is aware of and their configured values if you have them. We've got the environment endpoint, which tells me the environment variables, the system properties, etc., that the application is aware of. So server.ports, local server.port, sun.jnu, encoding, etc. We've got the loggers endpoint, which tells me all the different loggers, their levels, etc., and all their different contexts. You can change these. You can say that for COM example customers, I want this to be debug. For example, you can use a post instead of a git. We have a heap dump endpoint that gives us the heap of the application. Give me a heap dump, I can put that into a debugger. We have a thread dump, which tells me all the threads and whether they're waiting or not and what they're waiting on and so on. We have metrics, and metrics are keys and values. These are high cardinality data, things like HTTP requests, things like memory, etc. These are not individual requests. These are statistics about the overall system. And you can contribute custom requests here. You can custom metrics, right? You can actually add your own custom ones, or you can look at the existing ones, and you can see we have statistics like the count of them, how much it took, the max, etc. And any particular tags. Were there exceptions? What was the HTTP verb or the method? What URI did you get? You can actually break down the results by all these different dimensions, these different tags. This metrics endpoint is powered by something called Micrometer. Micrometer is a neutral metrics facade. It supports different time series databases, things like VMware's Wavefront, Prometheus, CloudWatch, Datadog, AppOptics, Google Cloud, Stackdriver Trace, etc. All these different ones, Graphite, all these different ones are supported by Micrometer. Here, we're not publishing the metrics to anything. They're just in memory here, but you can also very easily integrate a Micrometer integration, and it'll publish all these metrics that you capture automatically to a time series database. So all these different endpoints, the mappings endpoint shows me all the different HTTP URLs and how they relate to each other. So all these different endpoints give me information about the state of the service. One very useful endpoint that we haven't looked at yet is the health endpoint. Health tells me the health of the service. So here I can see that I have a file system, it's up. I have a liveness state, which is for Kubernetes. I have a ping. I have an R2DBC connection factory to my SQL database. All of this tells me how healthy these different subsystems are. If my database is down, then this will say down. And of course, you can control that state as well. So for example, let's suppose I have class availability change event controller, and I say post mapping down mono void. Okay. So I'm going to say private file application context. What's this? Why is it bouncing? It's okay. Okay, sure. Okay, so I'm going to build a REST controller. I'm going to use this event to publish. I'm going to publish an event in the application context, like so, right? So I'll say this.context, and I'll say I want to change the liveness state is broken. Okay, so in Kubernetes, when your service is deployed, you can configure a liveness probe and a readiness probe for your pods. The readiness probe tells Kubernetes whether your pod is ready to be put into production. Spring Boot can automatically configure these endpoints for you. It can also configure a liveness probe, which tells Kubernetes whether the service should stay working in production. Okay, so let's look at our endpoint here. Here's the Actuator health endpoint. Let's go to liveness. Okay, so it says up. Good. So now we say curl host localhost 8080/down, and then you can see it says down over there. I made this, and then I went over here and I refreshed. So it's very, very easy for your application code to signal that the service is sick, that something is wrong. And when this happens, the container orchestrator, Kubernetes, will shut down the application. Well, what happens when it shuts down the application? Does it kill your pod immediately, or does it give you some time to finish your work? If you wanted to wait for you to finish some work, you can use Graceful Shutdown. So that's what this is, Graceful Shutdown. You can easily configure that. You can say shut down equals graceful, okay? And here, the difference will be between sig term, which is not the same as sig kill, right? So when sig term happens, then you'll be given a period to wait. You'll be given a little interval, and you can configure that timeout per phase, right? And by default, I think it's like 30 seconds. And here it'll wait 30 seconds, and then it'll call sig kill on the pod. So this gives your application time to finish any in-flight transactions. But you of course have to specify this interval in your Kubernetes descriptors as well. Okay, so we've described how the service will run in Kubernetes, but we have to get the application into Kubernetes. One way we can do that is to use, we have to create a container. Don't be sad, we're not going to use Docker. We're not going to write YAML. It's fine, right? No, instead, we're going to use something called a build pack. Build packs are a technology that allow you to take your application artifact and transform that source code into an image that can run on any cloud. So it's a Cloud Native Computing Foundation project, and there's an implementation called Paketo. It's an implementation that lets you work very easily with lots of different technologies, Java, Go, PHP, whatever. And it's very simple. You can actually you can use Paketo to turn any application into a container, right? So, and you can use that with Spring, no problem. But Spring Boot has support out of the box. You don't even need to do that. So you can say maven clean package Spring Boot build -image, and that will work okay. But you see, that's going to create a Java application inside of a container. Our application can go faster if we use a native image, a Growl VM native image. So what I will do instead is I'll go to start.spring.io, and I'm going to add one more thing. I'm going to add the native support, Spring Native. Now this is experimental, okay? It's not yet GA. I'm going to copy and paste this here, paste, reload, and now that's going to it's going to add support for Growl VM native images using the Spring AOT Maven plugin. And I'll run this. Now this will take several minutes, so we're going to let this run in the background, and then I will go start a new module in the meantime. Okay. Growl VM, by the way, is a very nice technology. The idea with Growl VM is that there's this thing called native image builders. Native images are basically closed world architecture-specific binaries. The native image compiler will analyze the source code, and it will determine which classes are being used. The problem, of course, is that sometimes it looks at your source code and it sees that you're using this class and this class and this class, but all these other use cases that Growl VM, that Java applications support, like reflection, like dynamic proxies, like serialization, like loading resources from jars, all these things are in JNI, Java native interface, all these things it does not know about, right? And so as a result, Growl VM cannot easily turn your application into a native image. So you have to provide configuration. Spring Native, a project that we have built, will automatically provide that kind of configuration for your Spring applications. It teaches the Growl VM compiler about all the dynamic behavior of your application. So if you load a class like an application.properties from your jar, Spring Native writes the configuration to make that work. So all of that is done for you automatically, and it makes it, it makes the application compile into a native image. But that process takes a long time. It takes several minutes. So we're going to let that run in the background here. Now, while we're doing that, let's go build a new service. We have a service for our customer data. Let's build a new service for our order data, except that here, we're not going to use HTTP. We're going to use something called RSocket. RSocket is a binary protocol. It's a reactive binary network protocol that is the work of engineers from Netflix and from Facebook who want to build a protocol to get around the limitations of HTTP and gRPC. This protocol supports many different message exchange patterns. It's very, very efficient, and so on. So I'll say orders, and we're going to build an application now that when it starts up, will manage order data. So we have customers have orders, so it's a one-to-many, but this is not actually part of the aggregate, because even if you delete the customer data, you still keep the order data for financial accounting reasons, right? So it's a different service. At least to me, it's a design discussion. It doesn't matter, it's a domain, okay? So let's build a simple controller here. We're gonna build a class order RSocket controller, and the programming model for RSocket is very nice because we've integrated it into Spring. There's actually a direct integration in Spring itself. So order RSocket controller, here we are. And we're going to create a little in-memory database of orders. It's just dummy data, just sample data that we're going to use here. Okay, and it's going to be class order. Okay. Good. All right. So there's our dummy data, and I'm going to just write some sample data just as a simple example. So customer ID is less than or equal to 8, customer ID plus plus, var orders equals new array list order, for var order ID equals 1, order ID is less than or equal to some random number, right, times 100, etc., etc. Okay, so there's this, and we're just going to create some sample data for our domain model. Okay, and the order object that we're creating here will have integer ID and then customer ID. Good. 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 So that's our basic arrangement. And we're going to say that the ID is the order ID and then the customer ID. And the customer ID will match up with the IDs of the customer data. Uh-oh, what happened here? Okay, no, let's try this again. CD customers, Maven clean package, Spring Boot :build -image. Okay, run that. That run in the background. In the meantime, we remember when we ran this code before, we had 8 customers. So we're going to just have 8 records here. That's what I've done here is I've built 1 to 8. Okay. Okay, so now we have an RSocket, we have the data. Let's actually create an RSocket controller to expose that data so that we can consume it. And here we use message mapping. So I'm going to say orders.customer ID, publisher of orders, get for destination variable, integer customer ID. Okay, and I'll say this.db.get customer ID var orders. Okay, that's the orders data. And I want to say return a reactive stream from this iterable. All right, there's this. Let's see. New array list. Good. So what is the issue here now? Oh, publisher. Thank you. Okay, so I'm returning a reactive stream of data in our RSocket controller. So we can start this. In order to start this, we need to specify the RSocket server port. So RSocket server port will be, let's say, 8181. Good, that's running in the background. Okay, what happened? Terminal. Okay. Good, there's our RSocket service. Just like you can use curl to talk to a HTTP application, you can use RSocket. We can use RSC, which is like curl for RSocket. Localhost 8181. The route is going to be orders dot, let's say 2 for the customer ID, and the interaction model will be a stream. So when we do this, oops, did I go to the right port? RSocket server port. The route orders 2. Okay, sure. Uh-oh. Controller, message mapping, customer ID, get orders for, oh, friends, put customer ID, orders. Okay, of course. Okay. Oops. There we go. So there's our data for different records. Okay. So now we have an RSocket service, and hopefully soon we'll have a customer service. Maybe I'll start it here. in the IDE for now. Okay, good. So all of this is now running. We have our different services. Now I want to build a gateway. I want to build an edge service. And to do this, of course, I will go to start.spring.io. And here I'm going to build a new service called a gateway. And this gateway is going to be something that responds to requests from the outside world. So as the requests come in, I will handle them here, and I can adapt the outside requests to the downstream services here. Okay, so I'll use Lombok, I'll use the reactive web support, I'll use RSocket support, I'll use something called Spring Cloud Gateway, and so on. So I'm very happy with that. Let's hit generate. Okay. UAO gateway.zip. Oh, this is almost done as well. Okay, it's downloading the internet. I think what has happened, my friends, is you go to spring.io. Yep, Spring Boot 2.5 just went GA today. No, 20th, May 20th. So we have a new release of Spring Boot 2.5, and I'm pulling down new dependencies. Okay. So here's our gateway application, and this will be an edge service. It'll run on a different port. We'll say server port. Okay, port equals, let's say, 9999. And this will be the first port of call for requests that come into the gateway. We can do two things at the gateway. We can be an API adapter or an API gateway. API gateways act on the incoming requests, but don't change them, right? Oh dear, I just realized my computer's not plugged into power. They act on the incoming requests, but they don't change them, or they don't change the body. They just act on the generic envelope of the request. API gateways are easy to create using something called Spring Cloud Gateway. So I'm going to use gateway here, route locator builder, RLB. Okay. I say route, and what you do is you create as many routes as you want to define requests that go to the gateway and match the request. Let's see if this finished. Oh, okay. Well, before we do that, let's go over here and take a look at our Growl VM application. Here's the customer's application. I'm going to stop it here. This is finished. So now we can say docker run -p8080, and then we're going to run this Docker image. Okay. So you can see the application starts up in 150 milliseconds. So that's including the embedded database. Remember, I have H2, so I'm starting up a SQL 99 compliant database and the web server and all that stuff, and it's starting up in less than 1.5 tenths of a second, right? Very, very quick. The other thing that's nice about this is that the memory footprint is very low compared to the runtime of a JVM application. So the garbage collector of a Growl VM native image will have less, it doesn't work as quickly as the JVM itself, but it's so fast and so lightweight and so small a memory footprint that you can run many of these for very cheap. Instead of running one JVM, you can run 10 of these, right, or something like that. Very, 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 very small numbers. It'll take tens of megabytes of RAM, not hundreds, right? This is very, very powerful. So now we have our customer service, we have our order service. Let's go back to our gateway. Okay, good. So we're going to match incoming requests. We'll say route spec, and the request matches the incoming request. We're going to say when the request comes in to this path and to this host, then when that happens, then I want to process the request and send it on to the downstream gateway service, right? So 8080, and I want to send it to the customer's endpoint. The problem, of course, is that the request will come in with this path on this with this host header, and so the path cannot be both. It cannot be customers/proxy. That doesn't exist. So we need to act on the incoming request and configure filters. So here we're going to change the downstream path like so. So it'll be proxy, /proxy comes in, sending the path to customers, right? And that way I don't need to do this. This is where the real power of Spring Cloud Gateway is these route specifications, right? So we can say, set the path. We can also add response headers, for example, HTTP headers, origin. We can do all sorts of interesting things. We can do retries. We can do request rate limiters, right? You can configure a rate limiter to slow down the number of requests that are sent downstream. We can configure all sorts of things. And you can also, of course, just configure a custom filter of any kind to act on the incoming request as it gets sent to the downstream service. This is an API gateway. It's like Kong or Nginx or something like that. It's very powerful, and you can do a lot of interesting things here. At VMware, we also have, this is all open source, but we also have a product, an Ingress controller for Kubernetes that's based on Spring Cloud Gateway as well. So you can store your routes in a CRD, a Kubernetes CRD, and those get applied to all your services as well. But either way, very, very powerful. There's also a YAML and property file based configuration mechanism. You don't have to use Java. Okay, here we go. Let's run this. There's also a custom Kotlin Dsl, which is also very nice. Okay, so curl -x host hello.spring.io HTTP localhost. This will be 9999/proxy. So before I do this, actually, let's do -v to see the details. And here I'm going to do hello.spring.com, right? Remember back here, I said spring.io. So wildcard spring.io. I'm going to do .com, and you'll see I get, localhost 9999. Oh, H. Okay, see it says 404. The request was not found. The service was not found. Okay, so now we change this, and there we can see we have the data. So it's worked, okay? Good, so now we have our Spring Cloud Gateway API, and you can also see that we have this access control allow origin header that was added automatically by the filter. So this is a great way to proxy downstream services. So if you have a service over here and another service over here, they can come together at the gateway, and you can make them available to your JavaScript clients and your iPhone clients, and you can add security, and you can do compression and rate limiting and retries and all that stuff in a single place without having to change all of your downstream services. Well, what if you want to change the, what if you want to take the data from service A and the data from service B and combine them and compose them in some way so that they do something interesting? Well, in this case, you have to act on the data. This is called an API adapter. And so we're going to do that now here as well. We're going to create an API adapter. Okay. So here's our CRM client, and our CRM client will act as a proxy for the customer data and the order data from RSocket and from HTTP. So let's go back to our customer data here, and we're going to do something terrible, something that you should never ever do, not even when you're all by yourself at home and no one is looking. We will copy and paste code. So we go here. Okay, good. Customer. Oops, wrong one. There, gateway. And we go back to the order service. Copy and paste that as well. Here's the gateway. So now we have two client-side representations of the data. These are DTOs, or transfer objects. And now I can use them to build our CRM client. And the CRM client will have two important endpoints: publisher, customer, Git customers. And we're going to return a reactive stream empty for now, just for now. And we're going to get the order data. Get orders for integer customer ID. Return a reactive stream there as well, empty. Now let's implement these. Now remember, the HTTP endpoint is, the customer service is an HTTP endpoint. So we're going to use a non-blocking reactive web client, a non-blocking client. And we can do this using the Spring Framework web client, which is a non-blocking HTTP client. We need to create an instance of that here. So I'll create a bean web client. Okay. Now, we also need to inject a non-blocking RSocket client. The thing to remember, though, is that RSocket isn't a client service protocol. It's a bidirectional protocol. So when one side connects to the other, once they are connected, they stay connected. The sockets stay connected, and the sockets are multiplexed. They're reusable. Okay, so you don't have to reconnect each time. This makes communication much more efficient. It also means that you can share the same socket. So we don't talk about client server when we use RSocket. We say requester responder. But once connected, either side, both sides can make requests and produce responses. It's not just a client getting data from a server. Both can be client and server. So we also need to build an RSocket requester. Okay, RSocket requester. Good. And here you can see, since the protocol requires us to connect when the application starts up, since we only have one socket open, we just connect when the client is connected. When the object is created, we specify that at startup time, and it stays connected. You can configure automatic reconnections and things like this. You can use the RSocket broker from the Reactive Foundation, which is something that we work on. You can use that to do load balancing and smart proxying and all that. But the point is, you don't have to specify this over and over. Okay, let's do the HTTP one first. Localhost 8080/customers retrieve.body2flux customer.class. Okay, so there's our HTTP interaction. What about the RSocket one? Okay. Route, and it'll be orders.customer ID. I'm going to pass that in, and we're going to retrieve a stream of orders. Okay, so we have a reactive stream HTTP, and we have a reactive stream RSocket, but they're just publishers, and they can be composed together. It doesn't matter that they're different protocols. They're just publishers, even though some are asynchronous and non-blocking, and potentially. And by the way, this is an HTTP client. Remember that HTTP as a protocol does not understand back pressure. It doesn't understand reactive APIs. And so it doesn't matter if you use a reactive client with a non-reactive service. Like, let's suppose you're using like an old PHP service or something like that, right? And it doesn't understand non-blocking asynchronous communication. It doesn't matter, because the client will still be reactive. It won't waste threads in the client memory. It doesn't matter how the service is implemented, because there is no protocol level communication for back pressure. Okay, so now this code, both of these codes, this one here is customers, and this is the orders. Both of these assume that everything is going to be okay, right? The world's just fine. There's no failures on the internet. Nothing goes wrong. The network is infinitely fast. The service, the availability of the network is 100%, etc. And that's a very bad assumption. We should not make that assumption. So we want to make sure our service is a little bit more robust, okay? So what we can do is we can say, okay, well, when there is an exception, then we can control how to respond. Maybe in this case, we produce an empty reactive stream. We can also specify that, we want to retry the request if something goes wrong. Or maybe we want to retry it 10 times. Or maybe we want to retry it when, and then provide a backoff, right? And we can do a backoff in seconds here. We also can do a timeout. We can say I want to have a timeout for the request, and we can do of seconds, whatever. Okay, and these are operators that come with Project Reactor. These are not specific to the web client, so I can add those same ones here, right, for the RSocket communication. And you can see how easy it would be to put this in a generic handler, a filter, an operator, something like that. So these operators allow us to write code that is much more reliable, and they're built into reactive streams, so we don't have to use all these other libraries to do this, right? Now, these are just some of the very nice patterns that you can support with reactive APIs. Timeouts are a very good thing to have, but they're also not, I don't recommend them to be your first line of defense. You should only use them for the last resort, right? The last situation. Timeouts are a great way to guarantee that you don't waste too much time trying to call a downstream service. The problem, of course, is that sometimes you only get one shot. Like you make a request, it fails, then you use the timeout, it times out, and then you can try what? Maybe one more time before your client requires the SLA to kick in. Well, timeouts aren't great for that, right? If you want to guarantee, if you want to give as many opportunities, if you want to have as many opportunities to read the data, then you need something that is a little bit more robust. And so reactive programming makes it very easy, right? Like, let me just create a little example here. And we can look at a pattern that I love. Oh, whatever, void demo. Okay, so one pattern that's very common, let's imagine, just as an example, that you call a service, okay, to do. Let's say this is a web request or an RSocket request, and you're calling HTTP service. And you want to make sure that if that service fails, that you can try again. Well, of course, you could do a timeout. The problem is that you have to wait for the timeout, and then you have an SLA. Let's say that your client has an SLA of 10 seconds, which is a long time. That's a very long time, okay? And so that means that this service has an SLA. It has to produce a response within 5 seconds, right? Because you must retry one more time if it fails. Well, what if that thing has another call that it makes? Well, that service needs to produce a response in 2.5 seconds, right? And then that service itself, how much time does that have, right? It gets smaller and smaller and smaller, right? So the problem is that these timeouts put undue pressure. They reduce the time that each downstream service has to produce a response. So instead, you can use a pattern called hedging, right? Hedging. This is a very useful pattern in distributed systems. Uber and Netflix and Google all do this, right? And what they do is they make the same request to 3 different hosts and ports, right? And one thing you can use is a service registry, like a Spring Cloud's discovery client, right? So you can use Apache Zookeeper or HashiCorp Console or Netflix Eureka or whatever. The service registry allows you to programmatically ask for distinct instances. You can also ask for distinct A records from DNS, but either way, this is a great way to get more than one instance of a host and port. Okay, and then you can say, okay, I want to make the request to all 3 of the same service on different hosts and ports, and I want to get the fastest response. Well, think about that. That's hard code to write if you're not using reactive APIs. It involves, maybe a countdown latch and a cyclic barrier. There's threads and runnables and executors. It's very complicated code, but in this case, it's just very easy. So I can say, give me the first one to produce a response. First or fastest. Okay, and I get a string. I get a publisher of string, and I just pass in these 3 different ones. Whichever one returns first, we keep, and then we apply back pressure to the other ones. Okay, so I can now just use it. I can just say fastest dot subscribe and so on. So this is a very natural pattern that would not be easy to do without reactive programming. But okay, so now we've got our reactive streams, orders, and customers, and now I want to compose the data. I want to create a new view of the data, an aggregate. I want to do scatter, gather, service orchestration, and composition. So I'll say I'm going to create a new type, an aggregate type called customer, list of orders, list. Okay. There you go. So there's my aggregate type, my DTO, my wrapper, etc. Okay, good. So there's my aggregate type. And I want to now create a new view of that data. I'll say, give me a stream of customer orders. This is going to give me the customer data and the order data at the same time. The customer data comes from the customer HTTP service. The order data comes from the RSocket order service. So I'm going to say, give me the customers. And then for each one, customer, for each one, I want to keep in memory the current customer and then get all the order data. So I'm going to create a tuple. Okay, and I can do this using zip. And the zip operator takes two streams, left and right. The stream on the left will just be the customer. Okay. The stream on the right will be the order data. So get order for customer.getID. And I want to collect this as a list. Okay. And then what that gives me is a tuple. And here, T1 in my tuple is the customer. T2 is the list of customers. So I can say new customer orders, tuple dot get T1 dot get T2. Simple, right? Very easy to create. So there's my customer orders data. And now I can use that client to create a new view of the data. Let's go ahead and create a controller here. And final CRM client. Good. Good. So we're going to create a endpoint here to read the data. Okay. Let's restart that. Okay, so there's our service. Curl HTTP localhost 9999/COs JQ, whatever. Okay, so there's the, oops, what happened here? Orders.customer ID. What did I do wrong? Orders.customer ID. Orders. Let's see here. Something has gone wrong. I wonder what it is. This is on ports. Localhost 9191. Here's the order service. Oh, 80. Oh. I built it so that it returned a empty array when there's an error. Well, of course, it tried to make a connection. It connected to the wrong host and port, gave me an empty stream. So then in the response here, I saw the customer data, but no order data. So now I've just fixed it. Let's see what happens. So there's my customer data, order service. Order service is on port 9191 now. Now we go back to the gateway. Well, let's just see. There we go. So now you can see it says customer data is equal to ID 8 Spencer, and then customer ID is 8, 8, 8, etc. So I have the customer data and the order data for every single record. And that is a good example of where reactive programming is so powerful. It allows me to compose different streams of data in a very consistent, very clean, elegant way. There's not a lot of threading code here. There's no threading code. I don't have any Java lang thread, runnables, executors, countdown latches, phasers, semaphores, etc. None of that. It just works. It's also the most efficient version of the code. I'm not wasting any threads. And it's also the most reliable version of the code because I have these operators to make it easy to degrade gracefully. And I've done this all on top of a framework that makes it very easy to write code for Kubernetes, to containerize it, to turn it into a native image so that it's lightning fast, to add observability and distributed tracing and metrics and so on. My friends, we've only just begun to scratch the surface. Hopefully you got something out of this. I have been very happy to be here with you today. I know that we have only a little bit of time left, so I will happily answer questions. I want to thank you so much for being here. How do you say Teshakur, right? Is that right? I think it is. But thank you so much. I hope you're all healthy, happy, and safe, and I'll answer questions now.
Yeah, that's pretty cool, Josh. Thank you. And Teshakur.
Thank you.
There is one question I also forwarded from chat to you. It is how can we configure the gateway when we deploy to something like Kubernetes and don't know the IP address of our microservice? This question.
Yeah, so you can use either. Great question, by the way. You can use a service registry, right? A service registry can programmatically, the gateway can talk to the discovery client, and it can programmatically ask the service registry for all the different instances. Or of course you can use DNS, right? And DNS is a great fit as well. So either way, those are great ways to discover the IP address without knowing the IP address.
Yeah, and there is another question. Will Spring Native plus Growl VM just speed up the startup time and lower the memory footprint, or will also improve the application performance, e.g., faster calculations? Thanks.
As I understand it, the garbage collector is not as efficient with Growl VM, right? Because it's not the same JVM garbage collector. And so as a result, that might be less. You might get less requests per second with the native image. But like I said earlier, it's so small now. The native image is so small compared to the JVM one that you can run multiple instances at scale and still take up less RAM and less resources than the JVM one did before. So you can more than make up for the lost efficiency. But please test. It's I don't have any numbers on hand, so maybe it's also faster. Is there any way to use the gateway with Rabbitm Q? You mean like to proxy the Rabbitm Q messages? I'm not sure how you would do that. The gateway is HTTP and WebSocket. It doesn't speak AMQP, for example. It's a good question, though.
There's one more question.
Okay.
I will again forward it to you. Can we use Spring Batch with Reactive?
No, not really. Spring Batch is a long-running sequential data access-based technology. So it's one of the few projects in the Spring ecosystem that doesn't really have a great reactive story, right? Because when you're doing long-running sequential data access for like sequential data access with a SQL database or something, you're not usually doing it concurrently. You can send a request into a message channel and then use that message channel to, on a separate thread pool, run the Spring Batch code. Yeah, you can do that, but there's no reactive APIs really in Spring Batch itself. There are reactive APIs for Spring Security. There's reactive APIs for Spring integration, for Spring Data, for Spring Web, for Spring RSocket, for everything except for Spring Batch really, because it's a different use case. Another question about what do you think about using native images for serverless? That's a great fit, right? I don't really we have a project called Spring Cloud Function. Spring Cloud Function is a framework to adapt your functions, your Java lang functions, into handlers for serverless platforms like AWS Lambda and Azure Functions. We have a lot of different integrations there, and you can turn your function, your Spring Cloud Function, into a native image and deploy that. And so my friend over at Microsoft, Julien Dubois, he did a very good example showing using Azure Functions and Spring Cloud Function and Spring Native, for example. So it's a very good fit. In general, I tend to think that you should be cautious, because if your goal is to scale to 0, right? Is it really worth re-architecting everything to achieve that? I think if you can scale to 1, scaling up is easy. It's scaling down to 0 and then scaling back to 1 again. That's the hard part in this architecture, and it requires a lot of rethinking. So there are some use cases for which Spring Cloud Function is the best fit, and serverless is a good fit. But I would not rush to do that because it seems like a lot of extra work for possibly very little gain.
One more question. Do we lose, enter. Do we lose reactive streams power when we are stuck with a blocking classic database driver, or do we still can get value from reactive APIs?
Great question. So yes, you lose some of the power, but you can do it, right? It's still useful because it makes your programming life easier. It's consistent, so you have one kind of API. It makes it easier to compose. You also get these operators to make it so that you have a more reliable system. But yes, if you want to take data from a blocking classic database, you need to be careful to do that work on a separate scheduler. A scheduler is the reactive streams version of a thread pool, and this scheduler will, it's the thing that moves work from one thread to another. You need to make sure that you handle that carefully. Reactor supports that, but you don't want to do the work on the main reactive thread pool because that thread pool is a non-blocking event loop. So yeah, you don't get the scale, right? You don't get the scale if you do that, but you do get the ease of code. You get more consistent code and more reliable code. And there are ways to do it. You just have to be a little careful.
Yeah. One last question. What does the future hold for reactive programming and Spring Web Flux when Project Loom comes to Java?
I can't wait. Project Loom is very exciting because it means that now, remember I told you about there's 3 main use cases, right? 3 big features. There's resource efficiency, ease of composition, and reliability. Well, Project Loom solves the resource efficiency. Project Loom makes it so that it's now very cheap to create threads, right? It's not expensive, and so that's wonderful. But it still doesn't solve those other 2, which is reliability and ease of composition. So I think these things will mix together very nicely. It'll make reactive programming even more fun and more valuable, even more scalable. I can't wait.
Yeah, we have approximately 4 minutes, and yeah, there is another question. I'm going to forward it to you. Should we prefer R sockets over HTTP whenever possible?
Certainly, I think for service-to-service communication inside the data center, it's a great fit. There's also RSocket clients for C++, for Node, for Go, for all sorts of other languages. And think about like a large social network, right? Imagine you're a large social network like Facebook. That kind of communication at scale can be very valuable. To be able to reduce the cost of network I/O at that scale is very, very precious. It's very valuable. I think RSocket is a better protocol for services. Obviously, the open web is HTTP, and so because of that, RSocket can run on top of WebSockets, for example, if you have to do that, or you can use it on top of Aeron and so on. And you might want to create your service-to-service communications using RSocket, but then you have an adapter at the API layer, and that turns it into HTTP for the clients. I mean, you're not going to be able to ever get rid of HTTP, but yeah, I would prefer RSocket. I don't know why you wouldn't use that if you could.
Yeah. Any more questions? There are no questions right now in the question tab.
I hope that you all got something out of this. Please follow me on Twitter. I'm at StarbucksMan. Yeah. Thank you so much.
Yeah, thank you. Just one more question, if you want to answer. Can we have the demo code somewhere? They're asking the demo codes. Yeah.
Yeah, of course. GitHub.com. Hold on, I'll share my screen here. Okay, here. How can I share it in this chat? I don't know how to share it. Let me just share my screen, okay? Can you see my screen? It's right here.
Yes, we can see your screen, Josh. Yes.
Okay.
Yeah,
good.
it's pretty easy link.
Cloud Native Java -2021, Josh Long. Alrighty, well.
Yeah, I think we are okay for the questions. All the questions are answered. Thank you, Muhammed, Fatih, Borut, Yusuf, Barış, Kayhan, Moren for asking great questions.
Yeah.
And thank you, Josh. Very powerful workshop. Thank you so much. And very informative.
Thank you.
Yeah.
I hope we can get together safely someday soon, you know?
Yeah, so hopefully. Thank you.